Alright, in this video we will be going over section 9.2. Section 9.2 is about polar coordinates. First, I want to define something called the polar plane. Polar plane is a plane like the rectangular coordinate system. You draw two lines which are perpendicular to each other, and you mark this origin as the pole, and then this positive x-axis is labeled as polar axis. Okay, with this labeling, this plane is called the polar plane. Okay, next thing that we need to do is we need to know how to mark a given coordinate pair r comma theta on the polar plane. Okay, when you represent a coordinate pair r comma theta, this theta is the angular measurement and r is the sine distance from the origin. Okay, I will explain what we mean by the sine distance when we do examples. Before we go to examples, I want to define something called the direction specified by a given angle. Okay, for example, let's say your given angle is pi over 4. Then what do we mean by the direction specified by this given angle pi over 4? Okay, so first of all, you go to the polar plane. This is the polar axis and this is the pole. Then we need to figure out what is the direction specified by this angle pi over 4. First of all, notice that this angle pi over 4 is a positive angle because you have a positive sign in front. That means it should be a anti-clockwise rotation. Okay, so if I mark this angle in this polar plane, you will get an angle like this. This is the angle pi over 4. Notice that this total angle is pi over 2, so half of that should be pi over 4. Now, what I mean by the direction specified by pi over 4 is this direction. Okay, you draw this ray emanating from the pole, goes through the angle pi over 4. Okay, so this direction is called the direction specified by the angle pi over 4. Okay, so with that in mind, let's look at some examples. Okay, so here is the first example I want to take. Example, how do we mark the point 2 comma pi over 4 on the polar plane? 2 comma pi over 4. Well, to mark this point on the polar plane, first of all, let's draw the polar plane. Okay, this is my polar plane. This is of course the pole and this is the polar axis. Then how do we mark this point? The first thing you do is you mark the angle. Since my angle is a positive angle, it should be a anti-clockwise rotation. Okay, it is plus pi over 4. So I measure the angle pi over 4 in this direction, in the anti-clockwise direction. So this will be my angle. Okay, and this is the direction. This is the direction specified by my angle pi over 4. Okay, now I need to find the point, the location of the point. To find the location of the point, you look at your r. The value of r is plus in this case, right? As you can see, this is plus 2. If it is plus, you measure 2 units along this direction. Okay, along the direction specified by your angle pi over 4. Okay, if you measure 2 units, you get your point. Okay, I measure 2 units, say somewhere here. This length has to be 2 units, and this is the point 2 comma pi over 4. Okay, so this point is 2 comma pi over 4. Okay, let me do another example here. This time minus 2 comma pi over 4. How do we mark this point? As you can see in the second example, angle is same. Only r is different. Okay, r this time it's minus 2 instead of plus 2. How do we handle that? Well, first of all, you need to draw the polar plane, right? So this is your polar plane. First thing that you do is the first thing that you do is you measure this angle pi over 4. It's a positive angle, so you measure pi over 4 in the anti-clockwise direction. And then this is of course the direction is specified by that angle pi over 4. Okay, now how do we find the point corresponding to this coordinate pair? This time notice that your r is minus, right? Minus means this time you measure 2 units not along this direction. You measure the 2 units along the opposite direction. Okay, so this is the opposite direction, right? So you measure 2 units in the opposite direction, then you get your point here this time. Okay, make sure that this is 2 units. This length has to be 2 units. So this is the point that we are interested in. This point is nothing but minus 2 comma pi over 4. Okay, as you can see, if r is negative, then you have to measure that length specified by that number, the magnitude of that number in the opposite direction of the direction specified by the given angle. Okay, all right, let's move on and do more examples to understand this. Let's go over this example. Plot the points that have polar coordinates 2 comma pi over 3 and minus 1 comma minus pi over 3. Okay, let's work on the first point. Here is my polar plane, first of all. Now I need to mark this point. My angle, always you start by marking the angle. Okay, angle is positive pi over 3. That means it should be a counterclockwise angle. Okay, let's say pi over 3 is somewhere here, and this is of course the direction specified by the angle pi over 3. This angle is pi over 3. Now you need to find the point. Okay, how do you find the point? To find the point, you look at your r. See, r is positive in this case. So you measure 2 units along the same direction that your angle specifies. Okay, so if you measure 2 units along this ray, you will end up in a point somewhere here. Okay, so this has to be 2 units, and this point is nothing but 2 comma pi over 3. Okay, so that completes that one. And then let's go over the next part. We need to mark this point minus 1 comma minus pi over 2. As always, you start with your angle. This time the angle is minus pi over 2, right? So you measure your angle in the clockwise direction. If the angle is negative, you measure it in the clockwise direction. So if you do that, so where is minus pi over 2? Minus pi over 2 is all the way up to here, right? So this angle is minus pi over 2. It's minus because you measured it in the clockwise direction. So this will be minus pi over 2, and the direction is specified by that angle is this direction. Now how do we find the point? To find the point, you need to mark your r, right? R is negative in this case. So you have to measure 1 unit in the opposite direction. Okay, this is the direction specified by your angle, but you have to go in the opposite direction, 1 unit. Okay, if you measure 1 unit in the opposite direction, you will land somewhere here. Make sure that this is 1 unit. This length is 1 unit. Okay, this is the point minus 1 comma minus pi over 2. Okay, all right, that completes that example. Let's move on. Okay, next I want to go over this theorem 9.5, equivalent polar coordinates. Okay, so here is the first part of the theorem. The polar coordinates r comma theta plus 2 pi k represent the same point for every integer k. What does that mean? Is that true? Can we see that geometrically? Okay, first of all, let me walk you through the other two parts. The polar coordinates minus r comma theta plus pi represent the same point as the point r comma theta for any value of theta. And the third part is the polar coordinates 0 comma theta represent the pole for any value of theta. Okay, so that's the statement of the theorem 9.5. Let's see whether we can see this geometrically, whether we can see this is true geometrically. Okay, so what does the statement say again? The coordinate r comma theta plus 2 pi k represent the same point for every integer k. Is that true? Okay, every integer k means you get points like justification of part A. If you put k is equal to 0, it is just r comma theta. If you put k is equal to 1, r comma 2 pi, pardon me, theta plus 2 pi, r comma theta plus 2 pi, and then if you put k is equal to 2, you get r comma theta plus 4 pi, so on and so forth, right? Yeah, actually it should be r comma theta plus 2 pi. Okay, so are these points the same on the polar plane? Let's see. So if I draw the polar plane, let's say this is your polar plane, and suppose that your point r comma theta is this point. Then my question is this point same as r comma theta? Well, as you can see, r is the same, right? The sine distance from the origin is same, r. Only difference is here the angle is theta, here the angle is 2 pi, theta plus 2 pi, right? So here, this is the point corresponding to r comma theta. Then what is this point? Think about this point. To get this point, you have to add 2 pi to the existing angle theta, right? Where is theta plus 2 pi? Theta plus 2 pi is again here. Because this is already theta, this angle is theta, you have to add 2 pi to that to get theta plus 2 pi. To add in 2 pi means you go one full revolution. Going one full revolution means you are landing at the same point. Even if you add 4 pi, that means you go 2 full revolutions from this point. If you go 2 full revolutions, again you are at the same point. That means all these coordinate pairs mark the same point. Okay. All right, that's what the part 1 tells us. Okay, that's true even when you have minus signs here. Okay. Okay, the second part. What about the second part? The polar coordinate minus r comma theta plus pi represent the same point as r comma theta. Can we justify that? Well, B. Let's mark r comma theta. Let's say r comma theta is here. Then what is minus r comma theta plus pi? First of all, let's find the angle theta plus pi. Theta pi plus pi is this angle, right? It's clear. It is clearly this angle, theta plus pi. This angle is theta plus pi. That's because this angle is equal to this angle. Okay, this is already 180. Since this angle is theta, this total angle is pi plus theta or theta plus pi. Okay, now what do we need? Angle is theta plus pi but minus r. So this is the direction specified by the angle, but my r is negative, so you have to measure r units in the opposite direction. So you will land again on this point if you measure r units in the opposite direction. Okay, so this is the same point as, this point is the same point as r comma theta. All right, similarly you should be able to see that the polar coordinates 0 comma theta represent the pole for any value of theta, because r is 0, right? R is 0 means this length is 0. That length is 0 means you should be at the origin, right? For any angle theta, if r is 0, you are at the origin. That means you are at the pole. Okay. All right, that completes that example. This is kind of that theorem. This is kind of a idea of the proof geometrically. Okay, this is not a formal proof. Okay, the next theorem that I want to go over is converting from polar to rectangular coordinates. Okay, so here is the statement of the theorem, theorem 9.6. If a point in the plane is represented by r comma theta in the polar coordinates, then rectangular coordinates of the points are given by the pair x comma y, and x is given by r cosine theta and y is given by r sine theta. Okay, if you draw a picture, this should be obvious. So let's say this point is, the polar coordinates of the point is r comma theta. Okay, then how do you find the coordinate pair x comma y, where x is the x coordinate and y is the y coordinate? Well, for that you need to find this length, right? This length. We know that this is r, this length is r, this length is r, and this angle is theta. Then from simple trigonometry, we know that this length is r cosine theta, and this height is r sine theta. We all know that from the geometry of this right angle triangle. Okay, That means your x value is r cosine theta. This is the x coordinate, right? This length is the x coordinate. And this height is the y coordinate. So x is r cosine theta, y is r sine theta. Again, this is a simple geometric proof. Okay. And you can see that this proof works even when you have theta in other quadrants as well. Okay. For example, if you have a point somewhere here, you should be able to give the same justification. All right. So let's move on. Next, I want to go over this example. Find the rectangular coordinates of the point that have polar coordinates 2 comma pi over 3 and minus 1 comma minus pi over 3. Okay. So basically, we are given the polar coordinates. We need to find the corresponding rectangular coordinates. So here is the conversion. Here is how you convert from polar coordinates to rectangular coordinates. Okay, x is given by r cosine theta, y is given by r sine theta. Okay, let's use this conversion. Okay, to find rectangular coordinates, x is given by part A. I will call this part A. Okay, this is part B. R cosine theta, y is equal to r sine theta. Okay, so this is going to be r for the first point. Part A. Let's work on part A. R is 2. R is 2. So 2 cosine pi over 3. And your y value will be y is equal to 2 times sine pi over 3. Right? All what you need to do is you need to calculate these two quantities. Okay. So if you calculate these quantities, you should get x comma y is equal to 1 comma square root of 3, because if you simplify this by looking at trigonometric tables, this should be equal to 1 and this should be equal to square root of 3. So the point is x comma square root of 3. Okay. Similarly, you can calculate the other coordinate pair for the next example, next part. X comma y will be, I'll let you justify that, x comma y should be equal to 0 comma minus 1 in that example. Okay, please make sure that you justify it. Okay, let's move on. Next, the vice versa. Okay, how to convert from rectangular to polar. Remember, the previous theorem tells us how to convert from polar to rectangle. Okay, so this time we are going to convert from rectangular coordinates to polar coordinates. Here is the statement of the theorem. If a point in the plane is represented by x comma y in the rectangular coordinates, then the polar coordinates r comma theta of the point satisfy the following formulas. R squared should be equal to x squared plus y squared, and tan theta should be equal to y divided by x. Okay, that's how you convert rectangular to polar coordinates. Okay. All right, let's look at an example to understand this theorem. Here is the example that I want to look at. Convert the polar equation r is equal to cosine 2 theta to rectangular coordinates. Okay, how do we convert this to rectangular coordinates? Remember, we can use this theorem. Your r squared is equal to x squared plus y squared, tan theta is equal to y over x. Okay, so how can we use this theorem to find the rectangular equation here? First, here basically in most of these types of problems, when you convert polar coordinates to rectangular coordinates, you use trigonometric identities. Okay, first of all, notice that cosine 2 theta is equal to cosine square theta minus sine square theta. Okay, but by previous theorem we know that r is equal to, x is equal to r cosine theta, y is equal to r sine theta, right? So that means from the first equation we get cosine theta is equal to x divided by r, sine theta is equal to y divided by r. If you just divide both sides of this equation by r, you get this. Similarly, you get sine theta is equal to y divided by r. Okay, now I can plug in that here. I can plug in that here, but we are given that r is equal to cosine 2 theta. So let me write this cosine 2 theta is just r is equal to cosine square theta, that is x divided by r whole thing squared minus y divided by r whole thing squared. Remember, cosine theta is x over r, sine theta is y over r. Okay, so that's true. So if you square this one, what would you get? You get r cube is equal to x squared minus y squared, right? Of course, if you square this one, you get x squared over r squared. Here, y squared over r squared, and you multiply r squared to the other side, or you multiply both sides of the equation by r squared, then you get r cube in the left hand side. Okay, r cube is equal to x squared plus x squared minus y squared. But from the previous theorem, we know that r squared is exactly x squared plus y squared. But here we have r to the power 3, right? How do we tackle this now? Well, what we can do is we can find r from the previous equation. If you visit the previous equation, your r is going to be x squared plus y squared, the square root of that, plus or minus. Remember, when you take the square root, you have to put plus or minus. Okay, so this is the r, value of r. So now I'm going to go ahead and plug in this value of r over here. So if I plug that in, you get plus or minus square root of x squared plus y squared whole thing to the power 3 is equal to x squared minus y squared. Okay, this is the Cartesian equation. Okay, that completes that example. And of course, since you have an odd power here, you can pull this plus or minus outside. Okay, so if you pull that plus or minus outside, you get plus or minus x squared plus y squared, square root of that, to the power 3 is equal to x squared minus y squared. This is the Cartesian equation corresponding to the given polar equation. Okay, that completes that example. Let's keep moving. Again, I want to go over another example. Here is the example that I want to go over this time. Find all of the pairs of polar coordinates for the point with the rectangular coordinates 1 comma square root of 3. Okay, on the xy plane, 1 comma square root of 3. Where is that line? Okay, so let's say 1 is here, square root of 3 is the y coordinate. This is square root of 3, this is 1. Okay, so this is the point. All right, this is the point. Let me mark it. 1 comma square root of 3. Then how do you find all pairs of polar coordinates for this point? Okay, there could be more than one polar coordinate for the same point. Remember, in theorem 9.5, we know that all of these points represent the same point on the polar plane. Okay, r comma theta is same as the point r comma theta is same as r comma theta plus 2 pi, r comma theta plus 4 pi, so on and so forth. Okay, it marks the same point. Okay, so we need to find all the points corresponding to all the polar points corresponding to this Cartesian coordinates. Okay, so how do we do that? Well, again, we use this theorem. We know that r squared is x squared plus y squared. Notice that in the polar rectangular coordinates 1 comma square root of 3, this is your x, this is your y. Okay, so we make that observation. X is equal to 1 and y is equal to square root of 3. We know that x squared plus y squared is equal to r squared. Oh, r squared is equal to x squared plus y squared. That will give us 1 squared plus square root of 3 squared, which is 4. So r is plus or minus 2, right? The value of r is plus or minus 2. Either r can be plus 2 or minus 2. Okay, and then what about the angle? To mark the polar coordinates, we need the angle as well, right? In addition to r, we need the angle. because polar coordinates takes the form r comma theta. We are okay with r. We have two possible candidates. What about the angle? Well, this theorem again helps you to find the angle. Angle is given by tan theta is equal to y over x. Okay, we also know that tan theta is equal to y divided by x, that is square root of 3 divided by 1. That means there are two basic angles between in the interval 0 comma 2 pi, right? What are the two basic angles if you solve this trigonometric equation? That will give you square root of 3. Okay, you need to know a little bit of trigonometry from your pre-calculus class. So the two angles would be, one angle is pi over 3, the other angle is 4 pi over 3. Okay, please verify that. Those are the basic solutions on the interval 0 comma 2 pi. Okay, 4 pi over 3. Those are the two angles. Okay, so we have these two as candidates for the angle. So how do we mark this point though? What are the possibilities for this point? Possible polar coordinates for this point. Notice that one possible representation for this point will be in polar coordinates, this one, plus 2 comma pi over 3. It's clear. Okay, so this is the angle pi over 3, and then this length is measured in the direction where the angle specifies. So this point is same as 2 comma pi over 3 in polar plane. And when you write 2 comma pi over 3, remember you can always add 2 pi k to this one from the previous theorem that we discussed. Remember, all these points are same. Even if you add 2 pi k to your theta, that point is going to be the same. So I'm going to add 2 pi k to this. Pi over 3 plus 2 pi k. That will still be the same point as this point. Okay, this is one possible representation. Are there any other representations here? Well, yes. In this case, notice that we can work with this angle. This angle is pi over 3. This angle is pi over 3. And if you go to the other side, if I extend this line this way, notice that this total angle is 4 pi over 3. 4 pi over 3. That is this angle. Okay, this angle is 4 pi over 3. Now I can represent the same point, this point, with this angle. This is the direction is specified by that angle, bigger angle, 4 pi over 3. All I have to do is I make my radius or r negative this time, because I want to measure that in the opposite direction to get this point. To get this point, I cannot go in this direction, but I have to go in the opposite direction to catch this point. To do that, I'm going to make my r negative. Okay, so I can write this same point in a different notation. This time I put minus 2 comma 4 pi over 3. This is again the same point. I put some space here. I will tell you why. This should be clear to everyone. Okay, so this is the angle 4 pi over 3. Now if I measure minus, if my r is minus 2, I have to measure that length in the opposite direction here. Okay, so I will land on the same point. So this point is same as this point in the polar plane. So now I can add 2k pi to this angle. It should still be the same point from the previous theorem that we earlier discussed. So these are the two possible representations for the polar coordinates. Okay, polar coordinates corresponding to this point 1 comma square root of 3 in the Cartesian plane. All right, that completes that example. Let's move on. Okay, next I want to go over this theorem, theorem 9.8. Circles tangent to the coordinate axis at the pole. Okay, that means we have the coordinate axis like this. At the pole, the circles tangent to the coordinate axis at the pole means either a circle like this or a circle like this. Okay, both of the circles are tangent to the axis. Okay, for example, this tangents to the polar axis here, and this circle is tangent to the vertical axis. All right, let's go over the statement of the theorem. For a not equal to 0, the graphs of the equations r is equal to 2a cosine theta and r is equal to 2a sine theta are circles whose equations in the rectangular coordinates are given by x minus a squared plus y squared is equal to a squared and x squared plus y minus a squared is equal to a squared respectively. Okay, that means the Cartesian equation of this polar equation is this equation, and the Cartesian equation of this polar equation is this equation. Okay, so that's what it means. Okay, to understand this theorem, let's go over an example. Here is the example that I want to look at. Here is the example. Graph the equations r is equal to 4 cosine theta and r is equal to 5 cosecant theta. Okay, first let's deal with the first part, a. I'll call this a, first part. R is equal to 4 cosine theta. How do we draw the graph of Cartesian equation? Graph this equation. Okay, so to graph this equation, I'm going to find the Cartesian equation. Okay, I can use this theorem to find the corresponding rectangular equations in rectangular coordinates. Okay, maybe let me copy this to the other side. That will make our life easier because we can see the theorem directly. If I go here, here is the example that we are working on. Okay, now, so this is the polar equation. We need to find the Cartesian equation to graph this one. Okay, it would be easier to use Cartesian equation to graph this equation. So let's find the Cartesian equation of this one. Okay, rectangular equation in the rectangular coordinates. Okay, okay, how do we find the equation? Well, we can use this theorem. Okay, compare this against this one. Okay, so I can write this as this is equal to 2 times 2 cosine theta. That way you can identify the value of a. Your value of a is 2, right? This 2 should be in front by default. See, there's a 2 here. So value of a is 2. The value of a is 2. If the value of a is 2, you can find the equation of the circle using this equation. The equation of the circle is given by x minus a squared plus y squared is equal to a squared. Okay, so let's the equation of the circle. Equation of the circle is x minus a is 2 plus y squared is equal to 2 squared. Okay, so if you graph this one, you should be able to see that you get this circle, a circle like this. As you can see, that circle is tangent to the vertical axis. Okay, all right, what about the second part? The second part, my r is equal to 5 cosecant theta. Okay, that means r is equal to 5 over sine theta, because cosecant theta is 1 over sine theta, right? So that implies that this arrow indicates that it implies. Okay, this is the arrow we use for implies. This implies that r sine theta is equal to 5. What do you mean by r sine theta? Remember, from this theorem, from this particular theorem, converting between polar and rectangular coordinates, we know that r sine theta is exactly y. Okay, so I'm going to put y there. R sine theta is y, so that will give us y is equal to 5. Okay, how do you draw the graph of y is equal to 5? Go to the plane, y is equal to 5 is a line like this, right? This is the line y is equal to 5 with this coordinate being 5. It's a horizontal line. Okay, So that is the graph of this polar equation in the rectangular coordinates. All right, that completes that example, and actually that completes that section as well. I'll stop there and I'll see you next time.